Sorry
Yes,
about
sir.
that.
It's visible. Yeah.
Okay, okay. So today I am supposed to give a presentation on a very relevant topic, that is VLSI architectures for unconventional computing. So I think you may be aware of the VLSI program, MTech VLSI program here at Amrita. It is one of the oldest MTech programs in Amrita University, as well as perhaps it is one of the oldest VLSI programs in the country, because we started out in 2001. So we are more than, this particular program is more than 2 decades old. So we have our alumni spread across all the major chip making companies around the world, most notable among them being Intel, AMD, Qualcomm, you name it, right? Our alumni are there. So this is one of the most well-established MTech programs at Amrita. Okay, coming to today's topic, I think I would like to get started by bringing your attention to one of the major issues that is being faced by the industry, especially after the COVID pandemic has subsided. You might be aware that many industries, especially the automotive industry, they are facing a severe shortage of semiconductor chips, right? So that gives you a feel of the extent to which semiconductor chips have become part of any system, right? So traditionally, we used to associate the word computing more or less with computers. Always computing was associated with computers. You had all sorts of computers, starting from the desktop to the most sophisticated supercomputers. So computing was considered to be confined to the domains of different architectures of computers. But in the last couple of decades, with the advent of large-scale embedded systems, this definition of computing itself has changed. So we have computing systems present in almost any machine that we use. Let it be a car, let it be any household appliance, or let it be your smartphone, anything. So any machine that technology provides you will have a significant amount of computing involved in it. And this computing is realized using integrated circuits. So today, we will be looking at how computing has evolved and what is the place of VLSI, what is the place of VLSI design in the domain of computing, and why it has become relevant in the present technological scenario. So the agenda of the presentation is like this. We will start with traditional computing approaches. Then we will move on to how hardware has come to dominate the computing world. And finally, we will look at some hardware platforms that are being widely employed for computing in all sorts of machines. So we'll start with the basic stored program approach that all of us are familiar with. So that is called the Von-Neumann architecture. So all the traditional microprocessors which you find in your laptops or the desktop computers, all these basically follow the Von-Neumann architecture. In the Von-Neumann architecture, probably as you're aware, the program that controls the processor, which is the heart of the computer, will be stored in a memory, typically a RAM. And the instructions that make up this program, they will be fetched from the RAM. They will be executed in the processor, and the results of the execution of this instruction will be either stored back to the RAM or they will be output to some peripheral device. So this is how the traditional computers operate. And that is by and large applicable to even most of the computers that we use, even the laptops. Or of course, there have been a lot of enhancements to this architecture, but the basic processing follows the same approach. You have a stored program, you fetch instructions from the memory, you execute them, and you store the results back to memory, or you output it to some peripheral like a display or a printer or whatever. So the fundamental problem of this approach, of course, it has served us well for a very long time. But the basic problem of this approach lies in the fact that every instruction is accessed from the main memory. And irrespective of the speed of the processor that you are using, the main memory always has a speed mismatch with respect to the processor. Typically, all memories have at least a speed mismatch of about 10x. They are slower than the processor by at least a factor of 10 or perhaps even more. Now you might ask me why you can't make a memory as fast as the processor. It is not possible because there is always something called a speed area trade-off. If you try making a faster memory, you will have to lose on the storage capacity. So you cannot have both. As a result of which, in bulk memories which we use in RAMs, the access speed is much slower than the main processor. So this is one of the major bottlenecks in the speed of computation that can be achieved in any Von-Neumann machine. Of course, there have been a lot of attempts to improve upon this with some limited success, as we'll briefly see in one of the later slides. Another architecture which is slightly different from the Von-Neumann architecture is called the Harvard architecture. So I would not say that these two architectures are vastly different, because in the Harvard architecture also, the fundamental approach towards execution of programs is the same, which means that you have to fetch instructions from a memory. The only difference being that in Harvard architecture, the program memory and data memory are separated. So since you are not using the same memory for program and data, you need not wait for fetching the data, or you need not wait for fetching the instruction. You can carry out both these phases, the instruction fetch phase and the data fetch phase of the execution of an instruction can be carried out simultaneously, parallelly. As a result of which, there is considerable speed up of these processors when compared to traditional Von-Neumann processors. So all the current microcontrollers and all DSP processors which we use nowadays, almost all processors which are currently being used, they follow this architecture, where you don't share the program and data memory, rather you have separate memories and separate buses for accessing programs and accessing data. So this has yielded considerable performance improvement, but still we suffer from the memory bottleneck, because just as in the case of the Von-Neumann processor, here also we depend on memories which are considerably slower than the processor for storing both data and instructions. So from that perspective, from the perspective of memory bottleneck, we have not gained much by introducing the Harvard architecture. Though we have achieved a lot of other performance enhancements as a result of this tweak in the way programs and data are handled. So, round about the 80s, the late 80s, designers tried to conceive of various approaches for speeding up the processor, because the demand for faster and faster processors was increasing. And primarily, the approach of designers was to tweak either the Von-Neumann machine or the Harvard machine. That means they never attempted to change the fundamental way in which computing was carried out. They remained loyal to the Von-Neumann or Harvard approach, and staying within the framework of these two approaches, they tried a lot of performance enhancements. The first one was the reduced instruction set computing. So they reduced the number of instructions in a processor to a small set of instructions. The idea was that all the instructions will be made to execute in the same interval of time. There will be no multi-phase execution. The primary objective of developing the RISC philosophy was to make the processor amenable for pipelining. Because if you are sending the instruction through a pipeline, unless all the instructions execute at the same time, the pipeline will get kind of disrupted. So that was the basic idea behind the development of the RISC paradigm, the RISC philosophy. So the RISC approach was closely related to the pipeline methodology for enhancing performance of a processor. And they also tried increasing the size of the data and address. More word width or word size meant that data could be processed in a faster way. Suppose you have a 32-bit word. If you are using an 8-bit processor, you will need 4 cycles. Whereas if it's a 32-bit processor, the operation can be carried out in a single processing cycle. So that was one approach. And address words. They tried using larger address words so that larger memory space could be addressed. Another approach which was tried out, of course, it has become standard in all processors, was the use of caches. Cache memories are basically kind of buffers where you store data locations which are accessed more often. And these memories, they use technologies which provide faster access. Basically, they make use of the speed area trade-off. Their storage capacity is lesser, but they are faster. So the use of caches was another approach that was widely adopted for improving the performance of Von-Neumann and Harvard processors. Then, of course, application-based features were introduced, like in DSP processors, for instance. If you look at a DSP processor, you may have instructions dedicated for performing DSP operations, which you may not find in a mainstream processor. For instance, instructions for performing maybe convolution, which you may not find in a mainstream processor. So such application-specific instructions were introduced for enhancing the performance of these processors. Because if you are implementing such an operation in a mainstream processor, you may require several instructions, whereas you can execute the same using a single instruction in a DSP processor. And superscalar architectures were the next enhancement that was introduced, in which instructions could be executed out of order on the fly. So they were able to execute instructions in parallel. And the scheduling of the instructions could be done dynamically, depending on whether there was any dependence between these instructions. So all these methodologies were tried out for. And finally, clock frequency scaling also was done. with every generation of processors, the size of the transistors used was reduced, and the frequency of the processor, the frequency at which the processor was operating, was scaled up. So faster the frequency, the larger the rate at which the instructions execute. So if you look at the generations of processors that were introduced in the late 90s, you could see that with every generation, the frequency was continuously being scaled, and as a result of which there was significant performance enhancement. Okay, now what were the limitations of all these approaches? The first limitation was that whatever be the amount of pipelining or parallel processing that you try to do within a processor, if there are a lot of instructions which depend on each other, that means the outcome of one instruction is dependent on, the execution of one instruction is dependent on the outcome of the previous instruction, then obviously you cannot execute these instructions in parallel. So that was one major bottleneck in enhancing the performance of a processor, despite using all sorts of architectural approaches like pipelining and superscalar processing and so on and so forth. And another approach which I mentioned, that is the clock frequency scaling, that also was kind of tapering off, blindly increasing the clock. They found that it is not possible to scale up the clock beyond a certain extent, because as you know, probably those who have studied CMOS theory, they know that the faster rate at which you operate a CMOS circuit, the more power it dissipates. Higher power dissipation means more heat dissipation. And this will lead to reliability issues, because if a chip dissipates more heat, then it might even damage the interconnects and even the devices. You probably, many of you have learned about thermal runaway and stuff like that. So they realized that they have reached a limit as far as scaling up of clock frequency was concerned. And one more limitation of these processors was that they were not able to exploit task level parallelism in various applications. That means, suppose you have two different tasks, like browsing the web and running some background process like downloading a file. These are two independent processes. But if you use a traditional processor for executing these two in parallel, essentially what they do is they execute them sequentially, and they do it so fast that it gives a kind of illusion that they are executing in parallel. The reason is there is no other way of executing these tasks in parallel. So one of the approaches that was tried out was, of course, to use multi-processors. All the current processors that we use, they are multi-core processors. So there are several processor cores that operate concurrently. And we refer to the operation of these multiple cores as hardware multi-threading. Right? There are multiple threads running through all these processors. So this was one of the way that was suggested to exploit task level parallelism. Of course, that also had a lot of limitations. Even the use of multi-core processors had a lot of limitations, which I will come to in the next slide. So all these motivations, all these limitations basically motivated a completely different approach to computing. And this approach has been progressively tried out over the last 10 or 15 years, right? And the basic idea here is to replace software with hardware. When I say we replace software with hardware, basically what I mean is, when we are executing a task using a processor, we use a program which consists of several instructions. Whereas if you are executing the same task using hardware, we build a dedicated hardware for executing that operation. I'll give you a simple example. Suppose you want to multiply two numbers. In a traditional processor, you may have to store these numbers in two memory locations, you will have to fetch these numbers. You will have to store them in some local registers in the processor. And then you will have to execute a multiply instruction, or if the processor doesn't support direct multiply, you may have to execute the add instruction multiple times. And finally, with each iteration, you will have to update the partial result in some register. And finally, at the end of the multiplication process, you will have to store this register content, which holds the result, into a memory location. So probably this whole sequence of steps will take so many cycles, so many machine cycles. So essentially, the execution of the arithmetic operation, which is multiply in this case, is a sequential process. Now imagine that you are executing the same multiply operation using a multiplier, a hardware multiplier. Then you can complete the operation in a single cycle. Of course, the price that you pay is you use more hardware. You will have to have a dedicated hardware for performing the multiplication. But the flip side is that instead of several cycles, instead of expending several cycles, several clock cycles in completing the operation, you can finish off the whole task in a single cycle. So that is the basic idea, that is the gist of replacing software with hardware. So this approach is very effective because hardware is inherently parallel, as we have seen. It doesn't involve fetching multiple instructions. The hardware just executes the task in a single cycle. So this is the basic philosophy that is utilized behind using hardware for computing tasks. So we'll explore this approach, which is increasingly being used in all domains of computing. And that is where VLSI plays a very vital role, because the complexity of the hardware that is used in these applications, it is so high that we will have to implement these hardware in dedicated chips. And this requires a completely different design and implementation methodology that is totally divergent from traditional hardware design approaches. So one of the important ideas that is used in hardware implementation of computing is the exploitation of spatial and temporal locality. So by spatial locality, what we mean is, in any operation, suppose there are data that are stored physically close to each other, then we can use some dedicated hardware elements for executing operations based on these data. Similarly, temporal locality. Temporal locality means typically in many operations like DSP filtering, the operands that you will be using will be samples, data samples which are received in successive clock cycles. Right? You might have seen any filter equation. It will consist of a lot of samples like xn, xn minus 1, xn minus 2, and so on. So these are samples which are temporally close to each other. So these are two properties of many algorithms, many computing algorithms, which comes in very handy for hardware implementation, because you can create a lot of parallel elements which can exploit spatial locality. Similarly, you can use registers for storing data, and you can exploit temporal locality. So these two approaches are very widely used in architectures like systolic arrays, digital filters, FFT butterflies, and you name it. There are a lot of structures which make use of these approaches. So basically, they serve to enhance the performance of the computing algorithm. So another approach that we use is hardware reuse. That is, we use the same hardware for implementing successive tasks. We provide storage for intermediate results, and then we reuse the same hardware for executing successive tasks. Another approach which is widely used, especially in algorithms like neural networks, is called approximation. That means we compromise on the accuracy of the results. In applications where we don't require very accurate results, we use rounding off, and this results in significant savings in hardware. For instance, for a 32-bit operation, we can use 16 bits, and we can just pad the result with zeros with some loss of accuracy. If the application can tolerate, especially for instance, if it's an audio application, I think you know that if it's an audio application which involves hearing, the human ear is not very sensitive. So even if there is a loss of around 3 dB in the input signal, you are not going to be sensitive enough. So there can be some dilution, some loss of accuracy. And even if some samples are missed in between, it is not significantly going to change your experience, audio experience, unless you are looking for very high fidelity applications. So these are all techniques which are application dependent. Then you have shifting, right? Shifting, you know that shifting a number, a binary number to the left, basically multiplies the number by 2. That means you can exponentiate a number by an exponent of 2 if you shift it as many times. Similarly, shift to the right results in division of the number. So this is widely used in DSP applications for scaling up the data. Then you have something called stochastic computation. In stochastic computation, basically, we use a large stream of data. Whenever computations involving probabilities are involved, we make use of what is called signal probability. Signal probability means the duration for which a signal remains high. That is called the probability of the signal. So a stream of data can be used for representing a probability. And the advantage here is, if you send a digital stream of data through an AND gate, it results in multiplication of the probability. So you can see how simple it is. We can replace an entire multiplier with a simple AND gate. So in applications where probabilities are involved, like communication applications, inference applications. So in such applications, we can replace multiplication with AND gates. So this has spawned an entirely different field called stochastic computation, where basically we deal with probabilities instead of numbers. Then we have logarithmic computation. Of course, all of us know the advantage of logarithms, right? Because again, you are converting multiplication into addition. So if you have some means of computing the logarithm of a number, you can completely replace all multiplications with addition. And there are a host of other techniques. Of course, I am not going into the nitty-gritties of all these approaches. Basically, what I am trying to drive at is that hardware, dedicated use of hardware for specific algorithms can result in dramatic improvement of dramatic performance improvement in many systems. And that approach is being widely used in many applications. Okay, now we'll see some platforms in which all these techniques are employed. Of course, these are specific techniques which I referred to. Now, all these techniques are implemented in various hardware platforms. Some of the important ones we will examine now. Of course, the most important is FPGAs and ASICs. ASIC basically refers to application-specific integrated circuit. That means if you are designing and building a chip which is targeted at a specific application, as the name implies, it becomes an ASIC. Suppose you are making a video chip, an HDMI video chip dedicated for processing HDMI signals, then it becomes an HDMI ASIC, right? On the other hand, FPGAs basically stand for field programmable gate arrays. These are hardware platforms which can be programmed, which can be reconfigured for implementing any hardware functionality. So in VLSI design and in VLSI implementation, both these approaches are used. When we use ASICs, basically we use a dedicated die for realizing a particular hardware system. And once this is fabricated, the functionality of the die cannot be changed. On the other hand, if we are using an FPGA, it is reprogrammable. It is field programmable, where you can program the functionality in the field itself. So FPGAs have the advantage that they can be reprogrammed. So if you find a bug in your design, you can always reprogram the FPGA for realizing a new design where the bug is corrected. On the other hand, if you are detecting a bug in an ASIC, the only option that you have is to recall all the chips. Of course, the trade-off is that when you are realizing a system in a ASIC, in a silicon die, it is highly optimized. That means you can ship the chips in very large numbers at very competitive costs. On the other hand, FPGAs are not area efficient because the reconfigurability itself results in more area overhead. At the same time, they have the advantage that they can be reprogrammed. So basically, it's a trade-off. And FPGAs cannot be made in large volumes because they are not cost effective. So if you want to ship commodity devices like microprocessors, because you know that automobiles, they use bulk microprocessors in bulk. Each automobile may use anywhere between 50 to 100 processors. So such semiconductor chips which are shipped in large numbers, they are good candidates for ASIC implementation. Whereas if you are going to ship some systems only in very small quantities, then it makes sense to realize them using, implement them using FPGAs. So these are two broad approaches which can be used for realizing large scale systems. And as far as the design flow is concerned, the FPGA as well as ASIC design flow, it is completely different from what you might have studied in your undergraduate program. Especially in the digital domain, in a basic course in digital design, you might have been exposed to truth table based design of digital systems. For small systems, this approach is fine. A few gates, systems involving a few digital gates can be designed using the truth table or Boolean equation approach. Whereas if you want to handle a very complex system, then this approach will not work. So we have a lot of other alternatives like the hardware description languages, HDLs, which enable the designer to represent the model of a system at the behavioral level. Similarly, you have high-level synthesis, where you can use a MATLAB code or a C++ code and directly translate it into a hardware architecture. Then you have embedded flow, where there is a processor, there is a core, either a single processor or more than one processor, and you can create a block-based design consisting of this processor and various peripherals. So all these approaches are being used in realizing hardware-based systems. Then of course you have the GPUs, which probably all of you are familiar. GPUs and GPUs, they are more or less the same. If you are using a GPU for general purpose applications, then it becomes a GPU. Then you have something called neuromorphic computing, which is basically inspired from the biological neuron. And probably neuromorphic computing is going to completely transform the way computing is done in hardware in the immediate future. So here basically we try to mimic the human neuron. And this can be implemented using various approaches, digital approaches, analog approaches, or even mixed signal approaches. So basically the idea is to emulate the behavior of the biological neuron. So here basically we have what is called the locality of computing, right? If you are using a neuron, most of the computing happens at the sensory level and very little information goes to the brain. There's quite a lot of local processing. And this is something which you can see even in edge computing. Quite a lot of computing happens at the sensor stage itself. It is made possible because of the growth in VLSI technology, because you can have most of the processing happening very close to the sensor. And only some of the data needs to be uploaded to the cloud. The advantage, the reason why it has become possible to have high complexity edge devices is that VLSI technology has grown to such an extent that very complex designs can be cost effectively implemented. So that is the reason why we can have computing very close to the edge. And neuromorphic computing is definitely going to transform edge computing to the next level. Another approach, which it's not really another approach, it is basically a method that is derived from FPGAs. We have what is called FPGA accelerators. So accelerators are dedicated hardware which are designed for implementing some frequently used operations. For instance, if you have an application where you have a lot of HDMI video processing, you can very well have an HDMI accelerator. So whenever there is an HDMI processing to be done, the processor will relinquish its control and hand over the control to the HDMI accelerator. And once this application is done, again the control will come back to the processor. So FPGAs are very widely used for implementing accelerators. And one of the major domains where acceleration is used is in machine learning. Right? So machine learning algorithms, basically they have quite a lot of parallelism. So they are ideal candidates for implementation using large scale parallel hardware. And this approach is being exploited by a lot of AI platforms. What I have shown here is an AI platform from Intel, which has Intel processors. It has FPGAs, which are used for primarily implementing the machine learning engines. You have inference engines, you have AI engines. So all these algorithms, basically they are very much amenable for hardware implementation. And this is the main reason why all processor companies have taken over FPGA vendors. I think you might be aware that the major FPGA manufacturers, primarily Xilinx and Altra, they have been taken over by processor vendors. Xilinx has been taken over by AMD, and Altra, a few years back, Altra was taken over by Intel. The reason was that these processor makers, they realized that many of the operations are best implemented in hardware rather than in the processor. So it makes sense to build platforms which integrate both traditional processors and parallel hardware. So as a result of this, now companies like Intel, they are offering dedicated hardware platforms for performance intensive applications like AI. And these platforms, they incorporate a huge amount of hardware acceleration. So that is the extent to which computing has evolved over the years. From basic desktop computers, now we have reached a stage where we have multiple processors We have multiple accelerators, and more importantly, one thing which I have missed is all these enhancements are possible only if you have proper communication. So we have a lot of dedicated bus technologies which facilitate high-speed computation, high-speed communication between the processors. For instance, you have a bus called AMBA AXI. This is a proprietary bus from ARM. Similarly, there are a lot of other bus technologies which facilitate very high-speed communication, because unless you have some means of communicating data fast, in a fast way, between various processing elements, it is going to slow down the overall computing performance. I mean, it's like having very nice buildings and very poor road facility. That's what you see in our cities. Like, we have all sorts of very high-tech buildings, skyscrapers, but our road network, our road communication network is very poor. So the same thing is applicable for the micro level also, or the nano level also. You can have a lot of very powerful processors, but unless you have some means of evacuating data efficiently between these processors, again you are going to have something like the memory bottleneck. You are going to have something called the communication bottleneck. So you have a lot of data which you have created as a result of computation, but you have no means of communicating these data. So communication, efficient communication between processors is as much important as enhancing the performance of the processor. So nowadays there are a lot of communication technologies which enable fast communication between various components inside the chip. I am not talking about off-chip communication. I am talking about on-chip communication. So in the future, you are going to have more and more dedicated hardware for computation, and new technologies are going to come up, especially, as I said, faster on-chip communication. Instead of dedicated wires for communication, we are going to use networks for communicating data between various subsystems in a chip. Then we are going to have increasing component of analog elements inside computing systems. And various new device technologies are going to come up. Of course, in the interest of time, I'm not going to elaborate on these technologies, but you can rest assured that computing is going to witness a massive transformation with the emergence of these technologies. So with this, I conclude my presentation. Thank you for your patience. Now I'll be happy to take a few questions.
Thank you, sir. Thank you so much. There is no question from the audience side. Thank you for joining us today.
Okay.
Thank you.
Thank you very much. Thank you.
Yes.
Thank you.